Welcome to 8.3 Trigonometric integrals. So today we're going to look at 5 cases. All right, we're going to kind of lump a couple together, but we'll also need to do some pre-calc reminders. So the first cases that we'll look at is when we're taking the integrals when we have an odd degree for cosine or sine, if we have an even degree for tangent or secant, and then what happens if sine or cosine is an even degree. All right, so one thing we can think about, at least for this first case, and we'll kind of talk about them as we go through, but when sine or cosine is an odd degree, what we are going to do is we're going to save one, so put one to the side, and we're going to convert the rest. Converting the rest meaning using some trig identities. So give yourself a second to pause the video and remind yourself of some of these trig identities. So the most common one, sine squared plus cosine squared is 1. Tangent squared plus 1 equals secant squared, or you can now solve for tangent squared, all right, by subtracting 1. Cotangent squared plus 1 is cosecant squared. Cosine of 2x, we could rewrite it as cosine squared minus sine squared. We could then convert cosine squared to 1 minus sine squared using that first identity and gathering everything. All right. Similarly, if we're using cosine of 2x equals 1 minus 2 sine squared, we could solve for sine squared by, over here, we would subtract 1 and divide by negative 2. Or we could simply change the signs and now have a positive 2 in the denominator. So again, pause, get these, and then we'll begin with our first example. Okay, our first example is dealing with cases 1 and 2, where sine and cosine have an odd degree. Okay, now our goal is to make integrating easier. Okay, so if we just had the integral of sine to the 5th power of x, we couldn't use a U substitution, and we're kind of stuck. Okay, so we need to make things easier so that we can use a U substitution. Okay, so remember, this is where we're going to save one of the signs. So I'm going to take out one sign, and we're going to convert the rest then. So I'm going to rewrite sine to the 5th as sine times sine to the 4th. Okay, so sine to the 4th is like saying sine squared squared. So now we can use that trig identity. Sine squared is 1 minus cosine squared. And don't forget that whole thing is squared. Now we can use a U substitution. If we let U be cosine, then du is negative sine dx. Okay, so now this works out nicely. So now we're just left with negative integral of 1 minus U squared squared. So foiling this binomial, all right, multiplying that out, and then we can go through and integrate this, and then finally we make our substitution back for U, which is cosine of x, all right, and then we get our final answer. So negative cosine x plus 2/3 cosine cubed x plus 1/5 cosine to the 5th of x plus c. So the whole goal here is to think about getting to that point where we can make a U substitution and then integrate nicely. Let's try the next example. Okay, so this time I have cosine and sine, all right? But a straight U substitution right here isn't necessarily going to work either. So what we do is we zoom in on the fact that, oh, cosine has an odd degree. Okay, so whichever function has an odd degree, that's where I'm going to kind of change it. I'm going to take a cosine out, and we're going to be left with cosine times cosine squared. Okay, now remember, what we have left is what we're going to convert. So now we use that trig identity from up above. What's cosine squared? Well, cosine squared is 1 minus sine squared. So now we just distribute that sine to the 4th inside there. Okay, so now we've made our lives easier where we can actually use a U substitution. So now if we let U be sine, then du is cosine dx. So that takes care of this guy, and then we can rewrite this inside as U to the 4th minus U to the 6th du. We can integrate this hopefully nice and easily, and now we make our substitution back for U. So we get sine to the 5th of x over 5 minus sine to the 7th of x over 7 plus c. So wrapping up, when sine and cosine have an odd degree, we take one of those functions out and we convert the rest of what we changed. All right, now let's take a look at example 2, where we're going to look at tangent and secant. Okay, and we're going to look at when, or what we can do here if they're odd. Okay, so kind of just a quick review. If secant is even, we're going to save a secant squared for du and let u be tangent of x. All right, and just a reminder, the derivative of secant is secant tangent. All right, okay, so let's kind of zoom in here. So here we have tangent cubed, secant to the 5th, and we're integrating this. So they're both odd. So if we take one function out of each of those, so I'm going to rewrite this as secant tangent. All right, we're going to take a tangent out, we're going to take a secant out, and we're left with tangent squared and secant to the 4th dx. Okay, so we want to think about, again, our U substitution. All right, so that kind of side note where I said, hey, remember the derivative of secant is secant tangent. So if I notice I've got the secant tangent, so if I can convert all of this to just be in terms of secant, that's going to make a U substitution much easier. So using those trig identities, I'm going to change tangent squared to be secant squared minus 1. And now what we can do is we can distribute that secant to the 4th to each of those guys inside. And we have the integral of secant tangent times secant to the 5th minus secant to the 4th dx. So now this makes for a nice, easy U substitution. If we let u be secant, then du is secant tangent. So it takes care of this piece, and then we are left with the integral of u to the 6th minus u to the 4th. And we can integrate that nicely. All right, substituting back in for our u, we get our final answer to be secant to the 7th of x over 7 minus secant to the 5th of x over 5 plus c. So again, it's all about creating a nice, easy U substitution. So going back to this side note, if we had an integral where the secant was even and we had a tangent in there as well, we would keep a secant squared and let that for the du portion, and we would let u be tangent of x because the derivative of tangent is secant squared. So it's just a matter of, again, making those U substitutions nice. Let's take a look at the last example on the next page. Okay, so this is case number 5 where sine and cosine are even. All right, so when we have that, what we want to do is we want to change, so if we have the integral of sine to the 4th of x dx, we want to change it to an odd power of cosine. So how are we going to do that? Well, the first thing we're going to do is let's rewrite sine to the 4th as sine squared squared. Okay, so the integral of sine squared squared. Now remember sine squared of x. I don't want to rewrite it as 1 minus cosine squared because we want an odd power of cosine. So we're going to use that other identity where sine squared is equal to 1 minus cosine of 2x over 2. So if we use that, okay, and we square, we square this quantity. Squaring the 1/2 is going to give us the 1/4 out front. And then squaring this binomial, we have the integral of 1 minus 2 cosine of 2x plus cosine squared of 2x dx. Okay, well, if we break it up, okay, we break up the integral of dx, 1/4 times, I can pull that 2 out, that's where we get the 1/2 of the integral of cosine of 2x dx, and then the 1/4 times the integral of cosine squared of 2x dx. This guy, no problem, right? We can integrate this guy. We can integrate this guy with the U substitution, u being 2x, and du then being 2 dx. All right, and we can go through that route. This one is the tricky one. We still have cosine squared of 2x. So this is where we need to make another substitution here. So if we do that, let me kind of show my side note over here. we're going to jump to reminding us, hey, the cosine squared of x is equal to 1 plus cosine of 2x, but keep in mind, we have the cosine squared of 2x, okay? So we need to then go say, okay, well that means cosine squared of 2x is going to be 1 plus cosine of 2 times 2x all over 2. So then we can make that substitution on back. And we get the integral of 1 plus cosine of 4x over 2. Okay, so just kind of cleaning everything up. So like I said, we can integrate this guy, no problem. We get x over 4. Integrating this middle piece with that U substitution, all right, and then substituting back in, we get minus 1/2 times 1/2 sine of 2x. Now we're going to integrate this piece. Well, we can pull the 1/2 out, okay? So if we pull that 1/2 out, we're at 1 over 8. And we can now integrate this guy using a nice substitute or U substitution. So we had to do a few trig identity substitutions so that we can get to a nice U substitution here. So now if U is 4x, du is 4dx, and we can integrate this whole piece. We get x over 8 from this first part, plus 1/8 times 1/4 sine of 4x plus c. So I already kind of substituted back. And we get our final answer here. So combining our like terms of x over 4 plus x over 8, we get 3x over 8 minus sine of 2x over 4 plus sine of 4x over 32 plus c. So all of these just allow us to make nice, easy U substitutions. But sometimes it takes a few steps to get there. If you have questions, let me know.